Good morning, everybody. My name is Hilal. I'm a chemical engineering student. Today, I'm going to present one of my thesis topics that I'm going to defend on coming April. So, this chapter is based on the hydrothermal carbonization of loblolly pine and the recycling of that processed water and how that will affect the whole system. So, let's take a look at the overview of my today's talk. So I'll give you a little bit of introduction, which will be really brief, and then talk about the hydrothermal carbonization and what I did with that, meaning the recycling of processed water. And I will show all my results that I got from that experiment and give some conclusions. So the hydrothermal carbonization of lignocellulosic biomass. So that's why I put this slide here. This is the only US data. So that shows in 2012 there were more than 400 billion of dry ton biomass available in the US. And that will include all the forest residues, then the agricultural residues like rice hull, corn stover, and also that energy crops, which is miscanthus, switchgrass. So this data only in the US. So think about the rest of the world. They have also this kind of residual biomasses and what we will do. And let's see what the nature do. This is the natural way of converting those biomasses to solid fuels. So it uses heat, it uses time and temperature to convert those biomasses to useful fuels. But as you know, this process takes like hundreds of years to convert all of these biomasses to coal. But what is the energy demand? Yeah, as you know, that's especially in the development in the Asia and the countries in the Africa, especially South Africa, China, and India. So their growth rate and the energy requirement by those countries is huge. So we can't rely only on those natural process to give us those coal. So this is one study from the International Energy Outlook that shows that Africa and the Asia will require 50% more energy by 2030. So we don't have that much time to provide all those energy required by these developing countries. And this is another study showed by the group of researchers from MIT, and they showed says 13% of the total energy demand by 2030 will come from these renewable sources. So renewable source, especially the biomass. So here is our process, the hydrothermal carbonization. It's not new. It has been there for more 50 years. But what is really matter for our process is very short residence times. I mean, very short reaction time process. So that's the advantage of this process. So what hydrothermal carbonization do? So you will have a hot compressed water. We can say subcritical water will never go is vapor state. So that's why the process called subcritical water. So you have a very short contact time, less than 20 minutes, what we do in our lab. And you have a very high pressure. So we have a very high pressure system that's 1 to 5 megapascal. And this is what our experiment really looks like. So we are testing mostly the indigenous biomass from southern Alabama. So that's the loblolly pine. So we use this loblolly pine with biomass to water ratio 5. So then put it in a power reactor, heat it to 200 to 260 degrees Celsius, and leave there for 5 minutes to complete the reaction. Then we have 3 different products. So we have here the gases, so there's the liquid products and the solid products. So the solid products, we are used to call it the biocoal. because look at the initial biomass color and the final one. So later I will show you why do we call it biocoal. So now the question is, this process is suitable for batch processes. So if we want to process in a continuous process, so what we will do, we need to recover the heat. We need to maximizing our utility, especially the water. Every single time we are using 1 to 5. So if we put 1 gram of biomass, we'll put 5 gram of water. So that's a big utility issues. So if we use reuse all the liquids after first reaction, then what will happen in the outcome of this biofuel or solid fuel or in the liquids? So that was my experiment and my thesis on it. So let's look at some results that so far I got. So this is the mass yield, and it's initial is 100%, so that's why it's a mass yield from 100%. And how we define the mass yield is very straightforward. We have dry pretreated biomass, and we had dry initial raw biomass. So it's the ratio of this